Elastic adherence,
No way. Wait. What is this? Alright.
So let's start. Okay, so spent about 50 minutes. Okay, I think we spent 2 classes about capacitor. So another 2 classes to finish this topic. Okay. So we done the introduction, capacitance. We haven't done with the second and third. Okay. Today we discuss about the energy. Okay. So as usual, recall back what you learned so far about capacitor. Okay, so what are the equations you learned? What is capacitance? Capacitance is defined as charge stored in each plate to the potential difference between the plates. Okay. There is one year they asked it's better to say stored energy instead of stored charge. Anybody? Why? It's not really proper to say that store charge, but it must say that stores energy. Why you can't say it's not logical to say that it's store charge? Anybody? Try to answer. Anybody? Why you can't say it's store charge? Because if this plate got positive 5 coulomb, the other plate got negative 5 coulomb. So the total charge is 0 coulomb, right? Positive 5, negative 5 is 0. Okay. So that is net charge stored is actually 0. Okay. You see, stores energy is more proper. Okay. So if you say in the exam, you say it stores charges, So far they won't penalize you, but best answer is to store energy. Okay, the examiners strict, they go for energy. Okay. Another one thing they ask, how capacitor stores energy? What mechanism make it to store energy? By doing work to separate the charges. Okay, please add into your notes. How capacitor stores energy? By doing work to separate the charges. Charges are separated. Okay, when two charges separated, work is done. Okay, so whatever work done, it stores as energy, potential energy. Okay, that's one. How capacitor stores charges? How capacitor store energy? By doing work to separate the charges, stores as potential energy. Okay. Okay. So just recap again. So after C equals to QOV, we found that can be connected in series and parallel. Okay. So recall back all the 6 formulas, you know. Okay. So the series 1 over C total is 1 over C1 plus 1 over C2 plus 1 over C3. Parallel is C total is C1 plus C2 plus C3. Right. Okay. Voltage for series is the same as last time for resistor. Then series what? V1 plus V2 plus V3. Parallel is, of course, the voltage is same. And now current for resistor, now here is charge. Charge in series is the same. Same charges. But then parallel, the total charge is actually the whole charge. All the 3 charges add up. So conclusion, you want to store lots of charges, connect them in parallel. Parallel, you get lots of charge. Okay, capacitance rises. Okay. Okay, now let's move from here. Okay, so whenever you purchase a capacitor, okay, the capacitor will state 2 values. Okay, of course, it stated how much is the capacitance. Let's say I put 40 microfarad. Let's say you stated the capacitance, and it stated the safe voltage. Maybe I put, let's say, 25 volt. So they put safe voltage, the voltage. That means what's the meaning of that 25 volt? You can't apply more than 25 volt to the capacitor. More than 25 volt, it explodes. Okay, the plate got vacuum. So if the charge builds up a lot, what happened? The charge can cross the plate. Okay? High potential, so explode. Okay, like lightning can happen. So in exam, what they'll do, they will give you a few capacitors. Let's say you have few 40 microfarad capacitors. Okay, you have, let's say, plenty of 40 microfarad capacitors in your hand, and 10. Let's say you have 10 40 microfarad capacitors. Okay, they want to use that 40 microfarad capacitors, but the power supply they use is 50 volt. They use a 50 volt power supply. They want a capacitance of how much? Let's say they want a capacitance of 200 microfarad. Okay, you have a power supply of 50 volt. Okay, you want to have a capacitance of 200 microfarad. Okay, but in your hand you have 40 microfarad capacitors. Okay, few. Okay, so how do you connect them so that you get 200 microfarad, the effective capacitance? At the same time, oh, I forgot to say something. Okay, yeah, we use this. Yeah, so the capacitance is 40 microfarad. The safe working voltage found to be 25 volt. So you want to fix at 50 volt power supply. So how do you connect the capacitors? You can use as many you would like, 40 microfarad. So you get 200 microfarad. At the same time, it's safe. You never explode. So how many in series? You want to get 200 microfarad. 5 in series. as long as never exceeds 25 volt. You put 5 in series, each going to get less than 25 volt, right? So it won't explode. So you must connect in such a way that it never explodes. At the same time, the total capacitance is 200 microfarad. You have to put maybe in series and parallel. Anybody can think about one connection? The voltage across the capacitance when you connect, not necessarily must be perfectly 25. It can be lower, it's fine. Okay? But cannot exceed 25. Okay? Exceed 25 is less than 25 is fine. Okay. Think about how the connection going to look like. 200 microfarad. You can use as many as 40 microfarad capacitors you like. Okay. Okay, 2 minutes for you. Effective capacitance must be 200. Each capacitor must have a voltage less than 25 volt. Connect them one arrangement, some series, some parallel. Two minutes for you. Power supply is 50 volt. You can discuss with your friends. You want 200 microfarad.
How much?
Capacitance you have lot 40 microfarad, 25 volt. Yes, very stable.
Can we change the battery?
Like 10 how much are you?
Five parallel.
Okay, so you have this is 40 microfarad. So if you connect two here, you got two in series. So 40. This what is the effective capacitance here? 20 microfarad, right? 1 over 40, 1 over 40. But is it safe? Each going to take 50 divided by 2, so both going to take 25 volt, 25 volt, right? So it's safe. Safe, But we want 200. So what do you do?
Times 20
Times 10. So this pattern need to be repeated maybe 10 times. Go for 10. One way. Right? So you get 200 microfarad and all the capacitors are safe. They achieve 25 volt. They save, they produce 200 microfarad. Okay. Okay. So this is how the question going to ask. Okay. They purposely give a big power supply. Capacitance given is as a capacitor of low voltage. So you have to arrange them in such a way that get the capacitance is required at the same time also. Okay. So we use about how many for this case? 20, 40 microfarad capacitors used. Okay, let me show you one pass here about like this. So I go to the pass here. Okay, so of course this is the electric field capacitance, the past year, the day we did. So this electric field and capacitance together. I'll scroll down. Yeah, this question. Page 3. Okay, come on, give us a try. Some capacitors are marked 48 microfarad, same working voltage 25 volt. Show how a number of capacitors may be connected to provide a capacitor of capacitance 48 microfarad, same working voltage is 50 volt. I mean the power supply is 50 volt. It was the connection.
Oh, is that one? Sorry. I think it's inside. Yeah.
Yes, some 40 capacitance 48 microfarad, 25 volt. The rating. They want you to draw a circuit which effective capacitance is 48 microfarad, but power supply, the voltage supplied is 50 volt. How do you connect the capacitance?
voltage supply. So total voltage there.
The power supply voltage assuming 50. Okay. 50 volt connected to a few capacitors where the effective capacitance is 48 microfarad. So you must connect such a way again the capacitors, each capacitor connected should not have voltage more than 25. Okay. What? 1 minute for you. If you're done with this, go ahead and
This is very.
That's correct.
So A is very easy, A should be easy. Okay. How many capacitors used for the A? 4. 4, right? Stop 2 down. 4. Right? All of you use 4, right? For the A? So the power supply is like 50 volt. So you have 2 here, 2 here, right? So this makes 24 microfarad. Both safe because both get 25 volt, 25 volt. But you want to get 48, so you have another branch safe. Right. It's a circuit. Okay. Little tricky one. Good try. Where is the capacitor estimate? Get 72 microfarad. State working voltage 25 volt. Power supply state. You're going to get 72 microfarad. Draw the arrangement.
Like plus another 1 hour again.
25. Supply
74.
72.
Supply.
Supply is 25.
Supply is 25.
No.
So the third one will explode.
you, your one.
So, what? Power supply is 27.
So why would I go now?
No, it won't, right?
It'll be less than.
Yeah. Yeah, you got 25 volt, right? Okay, so this case, the power supply is how much? Power supply is 25 volt. Yeah. So how the arrangement should be to get 72 microfarad. So each is 48, each capacitor. So you add another one here. Is it possible? This is 20, you can't write 24 plus 48, never get 72.
Add 2 more.
Yeah?
Add 2 more.
What are the two? So 24, 24, 24.
Yeah.
So in this case, you can have same as above, okay? And you can have another one here, okay? Right? So in this case, 25 volt is the power supply. So is it all of them safe? Each getting how many volt? 12.5 volt is fine, as long as less than 25 is safe. 12.5 is fine. And the effective capacitance is good to 72 microfarad. Okay. Okay, so this is how some questions they will ask. They change the power supply, they give a one standard capacitance which has a certain safe working voltage. They ask you the ratio. Okay, so you need to figure out. Okay. Any questions so far? Got the idea? Or you can use like this. This also works, right? You have one here, another two in parallel. Okay. I think this circuit also works, right? 48, 48 become 24, 24 plus. This is 48. Okay, no, doesn't work. Oh, doesn't work. Doesn't work, sorry. This doesn't work. Okay, class. So let me ask you another one. Arrangement. Okay, hope you got the idea. Okay. Another one question is, okay, let's say you have a power supply which the voltage can be varied. Okay, the voltage can be varied. You can vary the voltage. Okay, we have two capacitors connected in series. Okay, this is 20 microfarad, 20 volt. This is 40 microfarad. Also, rating is 20 volt. Okay. So 20 microfarad, 40 microfarad connected in series with a variable, the power supply which voltage can be varied. Now the question is, the voltage or the power supply rise slowly there until, okay, question, what is the maximum voltage you can apply so that all capacitors are safe, nothing is explodes?
40.
What is the maximum voltage you can apply?
40.
No way.
You rise the voltage slowly until
Yeah, 20 sir.
20 volt. You must have a reason. 20 volt. Think carefully. Okay, in other words, okay, before we go to that, You just rising the voltage until it explodes. One of them explodes. Okay. Which is going to explode first?
At the same time.
When you rise the voltage, okay, which is going to explode first? 20 microfarad or 40 microfarad?
20.
20. Several reasons. 20. How many of you say 20? You keep 1 minute for you think. 20 microfarad or 40 microfarad? Okay, heat is C equals to Q over VV. What is should be same for both of them? What quantity must be same? Voltage same? The voltage must be same for both of them.
No, not same.
Cannot be same, right? They are in series and they have a different capacitance.
Q is the same.
Q is the same.
So,
Yeah, cannot think. Q same, C equals to Q over V. Which is going to explode for that? C equals to Q over V, charge is same. Which is going to explode?
40. So,
40 microfarad. Why say 40?
because C is bigger, so V is inversely proportional to C.
Okay.
So V will be bigger.
You see?
That's all.
You select 40, if you select 40 because you said C is bigger. C is bigger. So, C is.
C is bigger and Q is constant. So that means the wait. Sorry,
Yeah,
sorry, the other way around.
20 explode. It's okay, research. So 20 microfarad? 20 microfarad.
Yeah.
Why 20? Because
C is smaller.
C is smaller, therefore voltage will be
Voltage will be bigger.
bigger, greater. You know, it's opposite of resistance. If you have a two resistor connector in series, which resistor will occupy greater voltage? Smaller resistance or the bigger resistance? Which resistor will use small voltage in series? 2 ohm, 4 ohm connected to a 6 volt. Which is going to take more voltage? 2 ohm or 4 ohm? 4 ohm, right? Big resistance takes big voltage. Okay? But in capacitor, the other way around. Small capacitance will take big voltage in series. Why do you need to take big voltage? Because you have to keep the same charge as the 40 microfarad. Okay? The charge is same. Okay? So 40 microfarad, a little voltage is enough for it to store certain amount of charge. But 20 microfarad needs high voltage to store the same amount of charge. C equals to QOV. Okay? If the capacitor is small, you need a high voltage to store the same amount of charge. Okay? So, point I'm trying to highlight here, in series, small capacitance will use high voltage. Okay? Why? You need high voltage to store the same amount of charge as the big capacitance. Okay? So which is going to blow first? 20 microfarad will blow first. Why will it blow first? Because you're going to attain the 20 volt earlier. Okay? There's 20 microfarad achieve 20 volts, 40 microfarad won't be 20 volts. Definitely low. Okay? So because both cap at 20 volts, the same working voltage, 20 microfarad is the resistance. Okay? Now, you go to the first question I asked you. Okay? Can you find out the maximum voltage to be used so that nothing goes? 1 minute, wait. Calculate for me. What is the maximum voltage you can apply here so that nothing goes? Rise the voltage. So what is the maximum you can go so that both can go safely? Who's limiting the maximum voltage? That's the hint. Who's limiting the maximum voltage? 20 microfarad or the 40?
20.
Okay. So that's the idea you need to think about. 50 limits the maximum voltage. Can you find the maximum voltage now? V max, Okay, get me. Just give me the number. 3 significantly. Okay, what is the maximum voltage, then we use here. 50 microfarad is the limiting. Yeah. So when P is max, the 20 microfarad must use the maximum voltage. Go to the limit already. Yeah, right? So when this P max, the 20 microfarad voltage is what? 20 volt. So and 20 microfarad is 20 volt. How much voltage you start by the 40 at that moment?
0.
0?
Half. That's 10.
This capacitor uses 20 volt. So this capacitor will use how many volt?
10.
10. Yeah, right. 10 volt, right? How you got it? Because charge is the same. Charge same, right? So charge same. So C1 V1 equals to C2 V2, right? Charge is same. Q1 Q2 same. Charge of course the same. So Q1 same as Q2. So what is that? C1 V1 equals to 2 V2. Yeah. So from here you can work out V1 is definitely 20 volt. C1 is 20 microfarad. Okay, yeah, you can find the V2, right? This is 40 microfarad. So V2 is how much? 10 volt. So 10 volt. 40 is 10 volt. 20 is 20 volt. 40 is 10 volt. So Vmax how much? What the Vmax you can apply? 30 volt. Put 30, both works safely. Put 30.1, 20 microfarad will explode. Okay, smaller capacitance will explode. Okay, the key idea is charge the same. Okay, charge the same. The charge same we find that. It's also quite a common question. Last answer. Okay. The last which will explode. Okay. Yeah. Why do we explode? As I said, any moment. Let's say you apply 10 volt here. You apply 10 volt here. Okay. You check the voltage is due. Calculate the voltage of it. 20 microfarad will always have high voltage. Why? Because as I said, charge is the same. Charge have to be the same, right? Series. So if the capacitor is small, the voltage must be high so that you have the same charge. Okay? That's right. The main point is small capacitance will have high voltage in series. Okay? Okay? So let me add another one question. The same circuit, okay, same circuit. Just now we found that 50 microfarad explode. The maximum voltage found to be 30 volt. Okay, now can you find what is the maximum voltage now? Okay, what will happen to the maximum voltage now if a third capacitor was connected parallel to the 40 microfarad? Okay, which is also 40 microfarad as a safe working voltage of 20 volt. Okay, find the new maximum voltage now. Another capacitor 40 microfarad 20 volts and parallel. Now we adjust the voltage. What is the new maximum voltage now?
No, in series you get that.
Also not 40. I had a friend who was
You had a potential that you don't think that
It's the legal spread out. That's like 5 years ago. Space. Wait, let me find the name.
Okay, very well. What is the new safe working voltage? 40 microfarad, 40 microfarad, 20 microfarad. Yes. What is the new safe working voltage? All of them at cap 20 volts. You can't exceed more than 20. So again, you have to identify which capacitor will blow first. 20, this 40, this 40. Okay, 1, 2, 3. Still 20, right? Still 20. Still 20 going to blow first. Okay? Because here now, these two capacitors merge. What is the effective capacitance? Greater, right? So 40 become 80. Now here capacitance is 80. So when the capacitance increases, you just need a very little voltage to stop a certain amount of charge. Yeah, 5 volts. So the same idea. The charge has to be the same. Charge has to be the same. So C1, V1 still same. C1 is 20 microfarad, and the maximum voltage across the leading capacitor is 20 microfarad. So this can go up to 20 for sure. Okay. So when this capacitor achieves 20 volt, what is the voltage of these two capacitors? 5. Yeah. 5. So charge same. Charge on the left is same as the right. The right both combine together. Combine series. So C1 is 20, V1 20 volt. C2 combined was not anymore 40, now it's how much? 80 now. 40. 80. What is the new voltage across this? So you get 5. 5. Right? So when this is 20 volt, this capacitor uses 5 volt, 5 volt. So what is the maximum voltage you can apply? The maximum voltage you can apply? 25 volt. 25 volt.
So it's fine because the total capacitance becomes.
Yeah. Why 5 volt? Because the capacitance of the C2 increases. Okay. So when in series, when a capacitance rises for one side, you're going to use less voltage compared to the opponent. Okay. Opponent will use more voltage. The opponent have to work harder to get the same charge thought. Okay, you got the idea, huh? Okay, let's see. Move on. Go to the another type. Another type they can ask is, let's say you have one capacitor which is 100 microfarad. It was charged to 100 volt. It was charged to 100 volt. Okay, so the capacitor was charged. It's fully charged. Okay, this capacitor is fully charged. Okay, it's fully charged. Now this capacitor number 1 was connected. One was connected to another capacitor which is not charged. Okay, this is not charged. Not charged, which has a capacitance of 50 microfarad. Okay. The first capacitor is this, fully charged. Okay. So one capacitor fully charged is connected to another capacitor which is not charged. Okay. So what will happen? Charge, not charged. Okay. The charge is like a battery. Capacitor is a power supply. So what will happen? The charge will flow from the charged capacitor to the not charge. The charge starts to flow because there is a potential difference. It has a potential difference. Okay. The one has a potential difference of 100 volt. So if there is a potential difference and it's a closed circuit, current is started. The charge will flow. When the charge flows, the charge continuously will flow until what becomes same? What becomes same for both of them? Yeah? Yeah? The voltage becomes same. Okay? The voltage up and down becomes same. The potential difference zero, so no current flow. Now the question is, when equilibrium is achieved, what is the new voltage across the capacitor? 1. Find the new capacitor. New voltage, sorry. Find the new voltage. Okay. What is the new voltage for this arrangement? This is also another common question they ask. Okay. One charge, not charge, connected. What is the final voltage? So charge definitely flow from charge to the not charge until the voltage becomes same. So voltage of the above capacitor will decrease. The new capacitor will gain some voltage because now here it stops some charges. Okay. Until the voltage same, current stops. What is the new voltage? Okay. So I give you 2 minutes again. Try to figure out.
There's a, I think it's 66.7.
66.7. One of your friends says 66.7 volt voltage. As we see, you got 66.7. Charge, not charge. So if you connect these two capacitors, this is series of parallel. This is considered parallel. Effective capacitance become two capacitors together. How much the total capacitance now? 150. 150. Yeah.
So why did not series
Because the voltage becomes same. Voltage same only for parallel.
Answer correct.
Oh, I haven't checked. Okay. So let's see. So you consider this as a parallel capacitor. So the total capacitance last time was 100. Now because it's two connected in parallel, the effective capacitance become 150, 150, 100 plus 150. So now the new capacitance is 150. Okay. So what is the voltage across this capacitor should be? What is same for the previous circuit and the earlier circuit now? What quantity is same? Before charge is same. Charge conserved. The charge at the beginning is the same charge now started. Just relocate it. Okay? But the total charge is the same. Okay? So the clue again is the charge. Okay? So the charge for the first one is how much? Q equals to CV, right? C times V. So the original capacitance is how much? 100 microfarad times the voltage is 100. So it's 10,000 microcoulomb. Okay, the total charge stored in the early case is 10,000 microcoulomb. So the charge stored in this system also, the total charge is 10,000 microcoulomb. And as now new capacitance of how much? New capacitance how much? 150 microfarad. So what is the new voltage will be? So So what the new voltage will be? Just what formula is? C equals to Q over V. The new capacitance give you the new voltage. This is the total charge we get it. So it's the same. So the V new voltage is the new capacitance times the total voltage. New capacitance is 150 multiplied by 10,000 microfarad, microcoulomb. What do you got?
Oh yeah, yes.
Yeah, sorry, divide. Divide. Q is divided by C. Sorry. So V new is Q divided by C. Right? So 10,000 divided by 150. So what do you got? Very good. 66.7. So 66.7. Okay. This should be the new voltage. Okay. So what do you need to calculate first? A charge is connected to the charge. Remember the total charge is here. Okay. Find the total charge first. And find the new capacitance. Okay, parallel. You know the total charge is same. So you know the charge, you know the new capacitance. And find the new voltage. Okay. Yeah. Any questions? Okay, class. So let's go to the okay. So another 5 minutes. You know, because capacitors store charge, actually, as I say, it's not proper store energy. It's actually store energy. Now we want to calculate how much of energy stored by a capacitor. A certain amount of charge stored. So now we're going to calculate the energy of the capacitor. Okay, the last equation for this topic. When a battery releases energy charge, that means releases energy. Okay. For the battery, sorry. Okay. This is the V versus Q. Just give me a minute. Okay. You see, for the battery, for the case of battery, if I plot V versus Q for the battery, okay, if I plot V versus Q for the battery, okay, voltage across the battery and the charge it releases, how the graph going to look like for the battery? The voltage of the battery is always constant, right? Voltage of the battery never drops. So the area under graph represents what? The area under graph represents what? V versus Q. Your AS knowledge is the energy, right? V is what? V is energy per unit charge. So energy is what? VQ, right? So V versus Q, the area in the graph is energy, right? So the energy released by the battery is QV, QV, or area in the graph of V versus Q. Okay. So the energy released by the battery is QV, QV or VQ. But how the capacitor voltage versus Q graph looks like? V versus Q for the capacitor. How the V versus Q for the capacitor looks like, capacitor. And the battery is 10 volts. Before it charge, capacitor has a voltage of how much? 0, right? And you allow to charge to flow, The capacitor voltage will rise from 0, slowly rise to 10 volt, right? So how the V versus Q for the capacitor looks like? A straight line, the specific gradient. V versus Q for capacitor. So what this gradient represents? Yeah. Second one is the V versus Q for capacitor. This one is V versus Q for the battery. Okay. The battery voltage constant, QV is the energy releases. Okay. But for capacitor, V versus Q is a straight line with a gradient. Okay, voltage rises. So what is the energy stored in the capacitor? This is the energy stored in the capacitor. The area in the graph of V versus Q is energy stored. What is the energy stored in the capacitor? Half QV. Half QV. Okay, that's the formula given here. The energy stored in the capacitor is half QV. Okay. So you know, if we replace the Q, C equals to Q over V, right? Replace the Q with CV, get another 2 forms. So the dominant one is RQ. Okay. Yep. Why you got that? Because capacitor, the voltage will change linearly with charge path. That's the definition, right? What is capacitance? What is capacitance? Capacitance is Q over V. So if when the voltage rises, the charges start increases. So it's a straight line. And the gradient represents what? V versus Q for capacitor. Gradient represents what? Cannot be gradient there. Which quantity of the graph represents the capacitance? The reciprocal of the gradient, right? Capacitance is what? Q over V. V over Q. The reciprocal of the gradient is your capacitance. So you have to capacitance is constant. So it should be a straight line. Okay. When you're charging a capacitor, what is the efficiency of this process? How many percent? When you use a battery to charge a capacitor, what is the efficiency of this charging process? How efficient it is? The battery releases QV, the energy stored is half QV. How efficient? 50%. The efficiency to charge a capacitor always 50%. Yeah. What happened to another 50%? Another 50% is still blamed to the heat energy generated, the energy lost to the connecting wires. Okay, but I would say it's funny, but it's found to be only perfectly 50% loss. Okay, for the sake of capacity. So efficiency is 50%. Always. Okay, so if they ask energy stored in the capacitor, so these are the 3 equations of efficiency is 50%. So one example. So come on. Last slide for today. Okay, now. Find the charge and energy stored by 1000 microfarad capacitor. The potential difference across is 6 volt, 12 volt. So think about what formula. So what formula comes in? The new formula just comes half QV. The two. QV cannot use because you don't know the you can find charge first. You find the charge, then you can use QV, half QV.
So versus C.
If they never ask you to find the charge, you know the capacitance and V, then you need to use half QV or you can use the other one, right? Half C. Oh, I got 3 times. Okay, so hope So you got the answer, so I hope you got these answers.
The second one.
Hope you, this is your mind, equation part.
Good.
Find the charge. And sorry, yeah. You can use RC if you want. RC square also can. Of square over U. So 3 versions. Okay, yeah, so these are the energies. The voltage double, the energy stored increased by how many times? When the voltage of the capacitor double, the energy stored increased by how many times? 4 times. Yeah. 4 times. Or you can evaluate that by using R CD square. V double, the energy increased by 4 times. So V square. Yeah. Oh, okay. So, stop here. Thanks. Nicholas, thanks. We stop here.
Ranjung is next door, actually, it's not. Maybe my phone is silent.
I want to go buy food.